Okay, in the last video, I was able to derive this integral, which I claimed is going to be instrumental in, in evaluating exotic integrals like integral of x to the x dx of all definite integrals, of course, from 0 to 1, right? You have integral of x to the minus x dx, or you can even have integral from 0 to 1 of x to the x squared dx, or integral from 0 to 1 x to the square root of x dx, right? So like, you might be, you will already know how to evaluate integrals using your calculus. But imagine like someone, someone you meet in the street and then holding a gun in your hand, and he will say, oh, evaluate integral 0 to 1 x to the x. And you're like, oh, I haven't seen that before. So how are you gonna evaluate that, right? So here, as I promised, I'm gonna show you how to utilize the first equation here, this identity, to be able to evaluate these integrals. Now, we won't be evaluating all of these exotic looking integrals, but I'll be showing you a unified way to tackle all of them, okay? And to do so, I will consider the expression x to the c, x to the a. And as you can see, c and a here are constants, and for various values of c and a, you're able to recover these integrands. For example, c equals 1, a equals 1, you get x to the x. c equals 1, a equals 2, you get x to the x squared, and so on, okay? And this, we will rewrite it in the same way that we rewrite x to the x when we evaluate its derivative, and that is in terms of an exponential. So you can write this as e to the ln x of c x to the a, which, using the property of the logarithm, can be further written as e to the cx to the a ln, okay, ln of x, all right? So now that we have that, we will now be using a very important series expansion for the exponential, which is e to the y. So you can always write that into a series form, and that is given by 1 plus y plus y squared over 2 factorial plus y cubed over 3 factorial, and so on, all right? So since our x to the cx to the a here, we were able to write it in terms of the exponential, then it follows that we are also able to expand it. So x cx to the a, which we wrote in terms of the exponential, we will now be expanding this using the series expansion for e, noting that instead of just having y here, you have here the complicated term cx to the a ln x, okay? But that doesn't matter, you just substitute it. So you have 1 plus cx to the a ln x plus 1 over 2 factorial, so you have y squared, just the square of this term, c squared x to the 2a ln squared x plus 1 over 3 factorial y cubed, so you have c cubed x to the 3a ln 3x, and so on. So you can go as long as you want, but let me stop at the fourth term, okay? So now that we've done that, what we really want to do, now that we've expanded that, what we're really interested in is the definite integral of x to the c x to the a dx, okay? And like I said, for different values of c and a, we recover those various exotic integrals that we've seen in the previous page there, okay? So what we do is, since we have a series expansion for this one, we insert the series expansion inside the integrand. So this one we insert inside the integrand, and then we integrate term by term, okay? So now you have integral from 0 to 1 of dx, all right, plus c integral from 0 to 1 of x to the a ln x dx plus, so you have 1 over 2 factorial c squared integral from 0 to 1 of x to a ln squared x dx plus, so you have 1 over 3 factorial c cubed integral from 0 to 1 of x to the 3a ln cube x dx, and so on. Okay, and now this is where the magic happened, because now we can actually use, if you recall, the identity that we've shown in the first page. Let me write that here: x to the m ln to the n x dx, which we said was equal to negative 1 to the n factorial over m plus 1 n plus 1. Okay, now as you can see, this exact general integral here, these are just the, the terms for the expansion, barring the first term. The first term is a trivial integration. This is just equal to 1. But here, these are the various forms of this general integration for different values of m and n. So for instance, this first integrand, this is just when m equals a, n equals 1. The second integrand, this is just this one, but for m equals 2a, n equals 2. This one is just for m equals 3a, n equals 3, and so on. Okay, so now we've actually found the key in decrypting this integral using this identity that I've told you is gonna be important in solving the exotic integrals that I've shown. All right, so we use these different values for m and a. So now we can go back to this definite integral and evaluate it term by term using this identity. So the first term is just 1, and then the next term is, so since n is equal to 1, you have a minus sign there, so you have minus m is a, so you have in the denominator a plus 1, n is 1, so this is squared, and you have a factor there of c, alright, because n factorial is equal to 1. The second term, m is 2a, so you have 2a plus 1, n here is 2, so you have 2 plus 1 is 3, so that becomes cube, over, note that you have a, here, if you look here, you still have a factor of c squared, so let me write that here, c squared over 2 factorial, but then you have negative 1 squared because n is 2, and then 2 factorial, okay, so as you can note there, 2 factorial will cancel. The fourth term is, so m is 3a, so you have 3a plus 1 to the fourth because n equals 3, and then you have 3 factorial, negative 1 to the 3 is minus 1, so that's why you have the negative sign there, and of course we still have this factor c cubed over 3 factorial, so the factorial will cancel, and so on. Okay, and so now we can simplify this to give us 1 minus c over a plus 1 squared, so the factorials will cancel. This will give you in the denominator 2a plus 1 cubed, and then c squared in the numerator. For the fourth term, we have 3a plus 1 to the fourth in the denominator, and then c cubed, and so on. So you get the pattern, okay? And so basically, you've now solved this integral because you now have a series solution. This is a number now. This is now the definite integral of this one, okay? And so now, you can now see that for various values of c and a, you can just use this series expansion to evaluate those exotic forms. So, for example, if you let c equals 1, a equals 1, you recover the definite integral x to the x, right? C is 1, A is 1. But you know that it's just equal to this series, so you just substitute c equals 1, a equals 1. So what does that give you? You have 1 minus 1 over 2 squared plus 1 over 3 cubed minus 1 over 4 to the fourth. So that should be simple because c is 1, a is 1, okay, and so on. And you should see the pattern, okay? So in fact, this is exactly the answer that John Bernoulli was able to find in the late 1600s, but I should tell you that he didn't use this technique exactly. He used a repeated integration by parts, but you know, that was way harder. But this is how a modern, you know, calculus student would do it. Okay, at least a simpler way. So now, if you let's say c equals -1, a equals 1, what does that give you? That gives you the integral from 0 to 1 of x to the minus x. Well, you just begin substituting c equals -1, a equals 1. So that gives you a plus 1 over 2 squared plus 1 over 3 cubed. And -1 cubed is -1. This is a minus sign, so that becomes plus 1 over 4 cubed, and so on. Which, in fact, if you really want, you can write it in a closed summation form, the sum from k equals 1 to infinity of, let's say, k to the minus k. Okay, and the very fascinating thing about this is that the form of the summation k to the minus k exactly looks like the form of the integrand x to the minus x. So that is very awesome. And in fact, since it looks very, you know, symmetric, they call it the sophomore's dream. So it's something that it looks too good to be true, but in this case it is true, because, you know, we have like a freshman's dream. This is called so let's say x plus y squared. So typically people would expand it as x squared plus y squared. So that looks too good to be true, but if in fact that is erroneous, that's wrong. Okay, so we call that the freshman's dream. But here, this one on top here, integral of x to the minus x is just equal to the sum of k to the minus k. It looks too good to be true, but it turns out to be true in this case. Okay, so there. So I won't be showing you anymore like integral of x to the square root of x or x to the x squared, because what you'll just be doing is you'll just be substituting here the different values of c and a. Okay, but the thing is, you found a series solution for this definite integral. Okay, so that's it, and I hope you learned something new from this video. At least you now know how to integrate x to the x and then stump those fellow, you know, colleagues that you know who doesn't know the integral of x to the x, and then you can teach them how to do it and all its related exotic forms. Okay, so in the future video, I'm gonna do again maybe some other integrals that, you know, that I found amazing while I was studying physics. Okay, so I hope you check out the future videos, and I hope you learned something today. Thank you for watching.